I will create a folder and set up a virtual environment to install PyTorch and Jupyter. Now, I'll start up Jupyter Notebook to experiment with PyTorch Tensors. I'll create a notebook with Python 3 and name it PyTorch Tensors. Then, import Torch and print the version to make sure the import works without any issue. I will show you various ways to create PyTorch tensors from Python lists. Here is a Python list containing two nested Python lists, each with 3 elements. This is a 2 by 3 matrix. I'll create a PyTorch tensor with the Python list. x0 returns the first row. x1 returns the second row. x12 returns the value at the second row and the third column, which is 6. Let's check the data type of the PyTorch tensor by calling the dType attribute. It's 64-bit integer type. We can initialize a PyTorch tensor with float values. This time, the dType returns float 32. We can directly specify a data type when creating a PyTorch tensor, like so. Alternatively, we can use float tensor. Again, dType is float 32. Long tensor is for integer values, and we must ensure to pass compatible values. If we pass float values, we'll get an error. Let's try again with long tensor, passing integer values. This time it works fine. PyTorch has many built-in functions to create tensors. For example, we can create a tensor without initializing element values by calling the empty function. The values are whatever occupies the memory allocated for the tensor. We can create a tensor, initializing all elements to zeros, by calling the zeros function. Similarly, the ones function creates a tensor, initializing all elements to ones. We can use the zeros-like function to generate a tensor having the same shape as another tensor, with all elements set to zeros. The ones-like function generates a tensor having the same shape as another tensor, with all elements set to ones. The I function generates a 2D tensor, with ones on the diagonal elements. We can create a tensor with random values from a uniform distribution by calling the rand function. Each time calling the rand function will return different random values. The randin function generates random values following the standard normal distribution. Computers use a pseudorandom number generator, a deterministic algorithm for approximating a sequence of random numbers. An initial value called seed completely determines what sequence of numbers will be generated. With PyTorch tensors, we can set the seed to use the same sequence of numbers for repeated experiments for reproducibility, by calling the manual seed function. Again, I'll set the seed to the same value and call the rand function. The output shows the same values as the previous cell because we used the same seed to generate random numbers. The shape property returns the shape of a tensor. We can change the shape of a tensor by the reshape function. This is another example of reshaping a tensor. Let's look at how to create PyTorch tensors from NumPy arrays. As a reminder, we load NumPy as NP. We call from NumPy to create a PyTorch tensor from a NumPy array. Alternatively, we can create a PyTorch tensor by passing a NumPy array, like so. We can convert a PyTorch tensor data type by calling the type function passing the desired data type. dtype is float32 as expected. A PyTorch tensor created with the from NumPy function shares the same underlying data with the NumPy array. Here, I've modified the NumPy array after the PyTorch tensor was created. Yet, we see the same modification in the PyTorch tensor. However, a PyTorch tensor created with torch.tensor copies values from the NumPy array. Therefore, the modification I made to the NumPy array after the PyTorch tensor was created does not affect the PyTorch tensor at all. We can expose the values of a PyTorch tensor as a NumPy array by calling the NumPy function. The NumPy array created from the PyTorch tensor shares the same underlying values. Here, I've modified the NumPy array after it was created from the PyTorch tensor. Yet, we see the same modification in the PyTorch tensor. Now let's look at mathematical operations with PyTorch tensors. We can add a scalar value to a tensor by the plus operator. As you can see, every element is increment by 1. We can add two tensors, element by element. The add function also works to perform element-wise addition. The add underscore function performs an in-place addition. It modifies the values within the tensor. The in-place addition works between tensors too. Now, let's look at subtraction operations. We can subtract a scalar value from a tensor by the minus operator. As you can see, each element is decrement by 1. We can subtract a tensor from another tensor, element by element. The subfunction also works to perform element-wise subtraction. The sub underscore function performs an in-place subtraction. It modifies the values within the tensor. The in-place subtraction works between tensors too. Now, let's look at multiplication operations. We can multiply a tensor by a scalar using the multiplication operator. We can multiply a tensor by another tensor, element by element. The mul function also works to perform element-wise multiplication. The mul underscore function performs an in-place multiplication. It modifies the values within the tensor. The in-place multiplication works between tensors too. Now, let's look at division operations. We can divide a tensor by a scalar using the division operator. We can divide a tensor by another tensor, element by element. The div function also works to perform element-wise division. The div_ function performs an in-place division. It modifies the values within the tensor. However, it cannot modify the data type. The operation fails because the data type of the tensor is long, and the division would produce float values. Let's try the division again, using a float tensor. It works as expected. The in-place multiplication works between tensors, too. Now, let's look at dot product and matrix multiplication. The dot product operation performs element-wise multiplication, followed by the summation of all elements. It is also called a scalar product because the final output of the dot product operation is a scalar value. We can multiply a matrix by a vector, using the matrix vector multiplication. In this example, the matrix vector multiplication performs the dot product between each row vector of matrix M1 and vector V1. We can perform matrix-matrix multiplication. The operator is @mark. It calculates the dot product between each row vector of matrix M1 and each column vector of matrix M2. We can also use the function to perform the matrix-matrix multiplication. It's easy to calculate basic statistics using tensors. We can call the mean function to calculate the average of all elements in a tensor. The mean function accepts the dim argument in that we specify the operation direction. If we want to calculate an average for each column, we specify dim to 0, meaning the row direction. We specify dim to 1 to calculate averages along the column direction. The result shows an average value for each row. Standard deviation produces a single value that measures how spread observed values are from the mean. The std function calculates the standard deviation across all values. We specify dim to 0 to calculate standard deviations for each column. We specify dim to 1 to calculate a standard deviation for each row. Now, let's look at min, max, and argmax functions. The min function returns the minimum value within a tensor. The max function returns the maximum value within a tensor. The argmax function tells us which element has the maximum value. The values are considered to be flattened, row after row. Therefore, the index ranges from 0 to the number of elements -1. In this tensor, the first element has the largest value. So, it returns 0. Similarly, the argmin function returns the index of the minimum value within a tensor. We call the argmax function with dim equals 0 to perform the argmax operation for each column. We specify dim equals 1 to the argmax function to perform the argmax operation for each row. Whatever we can do with argmax, we can do with argmin. We specify dim equals 0 to the argmin function to perform the argmin operation for each column. We specify dim equals 1 to the argmin function to perform the argmin operation for each row. What do you think will happen if we specify dim equals 0 to the min function? It returns both minimum values and their indices for each column. We specify dim equals 1 for the max function to obtain both maximum values and indices for each row. There are many more operations we can perform with PyTorch tensors. Let's look at some of the commonly used ones. The fill_ function populates a tensor with a given value. It's an in-place operation. We can calculate the square roots of all elements in a tensor, like so. It is not an in-place operation, so the original tensor was not modified. There is also an in-place version of the square root function. Notice that it has the trailing underscore in the function name. The linspace function generates an evenly spaced sequence of numbers, given a start, an end, and a steps value. Here, I'm generating a sequence between 1 and 5 with 5 evenly spaced steps. The clamp function clamps values within a range. Here, I specify a minimum of 0.5 and a maximum of 1.0. Here, I'm using the randin function to generate random values following the standard normal distribution, which has a mean of 0 and a standard deviation of 1. The lower values will likely go lower than the minimum of 0.5. So, any value smaller than 0.5 becomes 0.5, and any value larger than 1.0 becomes 1.0. Although there is no value larger than 1.0 in this example of randomly generated values, if there is, they will be capped by 1.0. We can concatenate tensors. Here, I concatenate 2x2 tensors, x1 and x2, with dim equals 0 so that tensors are concatenated along the row direction. As you can see, concatenating the 2x2 tensors in the row direction produces a 4x2 tensor. Now, let's concatenate the 2x2 tensors along the column direction. We have a 2x4 tensor as a result. We can concatenate more than 2 tensors, like so. Concatenating the 3 2x2 tensors along the row direction produces a 6x2 tensor. We can concatenate the 3 2x2 tensors along the column direction with dim equals 1. It produces a 2x6 tensor. Now, let's try concatenating a 3x2 tensor with a 2x2 tensor along the row direction. Would that work? Yes, it works. It produces a 5x2 tensor. As we specified dim equals 0, we concatenate 2 tensors along the row direction, which means the 2 tensors must have the same number of columns. In other words, the concatenation only works if tensors have the same shape in the concatenating dimension. Here, the cat function is invoked in the column direction, but 2 tensors have a different number of rows. If we try concatenating the 2 tensors on a mismatched shape, it will cause an error. So, when concatenating tensors, make sure the concatenating shape matches among all tensors. There are many more ways to create PyTorch tensors and perform operations with them. Please refer to the link for details.